Today's lecture is going to be a bit more grounded in computer science. We're actually going to look at some code this time. Whoa. But it's still going to be very mathy. We're not going to go into pure data structures until a little while later. A big task in working with and understanding data structures is analyzing them, being able to tell how long they'll take to do certain operations, or how many resources they take in some other measure, like how much memory it uses, or even how much network traffic it requires. The first thing you might think of for how to measure this is to run the algorithm on your computer, time it, and then an algorithm that takes 5 minutes is probably better than an algorithm that takes an hour. But the problem with that is that there's so much variation in real computers that it's hard to get an objective measure of how good the algorithm is. There could be different computers with different specs, different operating systems. Maybe one is running a Bitcoin miner in the background. Too much can vary. We want to go into a nice, comfortable math world where we can know things objectively. In addition to that, the amount of time a single run of the algorithm takes often isn't very interesting information. We'd rather figure out how long the algorithm, or how quickly the algorithm's runtime grows as the input size grows. You might have an algorithm that works super duper fast when you run it on a list of 5 items, whereas that other algorithm seems to work much more slowly. But it's very possible that the algorithm that seemed fast at first could have runtime that just balloons out of control for larger inputs, and that algorithm that was slow initially could handle the increased number of inputs much more elegantly. We're going to spend a lot of time in this course formalizing the notion of an algorithm being efficient. And we're going to start with how to count the number of steps an algorithm takes. In the readings, it talked about different potential ways to measure the amount of steps an algorithm takes. Actually, I guess step is a term with a formal definition. I'm better off saying how much time an algorithm takes. And one of those methods was to count primitive operations, where primitive operation is roughly defined as something that would probably take one instruction in a reasonable assembly language. It's not very well defined, but it doesn't have to be, because we're quickly going to see that it is just a big hassle and gives you a lot of detail that you don't need. But let's try it anyway, just to show off how it works. What are we on, lecture 4? Oh yeah, so on line 1, we have an assignment. Writing to a variable takes 1 step. N has to be read. That's a memory access. Those are not 1 step. Those are each 1 primitive operation. And you have an addition. If you've taken Comp 2280 or a similar computer systems course, you can probably start to see these being roughly analogous to processor instructions. On line 2, we have another assignment, multiplication. We're pretending our computer has a multiplication operation. And then 2 variable reads for a total of 4 primitive operations. Line 3 reads B, and then this was a bit of a point of contention last time I gave this lecture, the slides say that it has one more step, comparing. And then this compare primitive operation sort of envelops the logic of like jumping or branching or not doing any of those things of the if. You could very well argue that the comparison between b and 0 is one primitive operation, and then determining whether to branch based on that is another. But that's kind of it's kind of an example of why we're not using primitive operations, because counting things based on primitive operations leads to dumb arguments like this. Whether or not an if constitutes an extra operation will not meaningfully affect how efficient your algorithm is. Anyway, assignment, read, subtraction. That's 3. Woohoo! So now we know exactly how many operations this little block of code does. But it was really clunky. It later turns out that the number of primitive operations doesn't really matter. We'll see later when we are analyzing code with loops that the number of times a loop is repeated has so much more of an impact on the runtime of an algorithm than any part of it that runs in a constant amount of time. So to make this more elegant, instead of counting primitive operations, we count steps, where one step is one line of code that contains a fixed number of primitive operations. So basically, a step is a line of code that isn't a loop. So check this out. Line 1 has one step because it's not a loop. Line 2 has one step because it's not a loop. Line 3 has one step because it's not a loop. Line 4, let me check my notes. It's one step. So much easier. And believe me, algorithm analysis is going to get very hard when we get into stuff like loops and functions, and if you go further into this sort of thing, recursion. So it's really nice to be able to sort of ignore these finer details that don't end up changing much. This might not be very meaningful with the amount of knowledge you have right now, but in this analysis, we found that it has 4 steps. And in this analysis, we found that it has, 7, 8, 9, 10, 11, 12 steps, approximately. I hope so. So 4 steps, 12 steps. With the stuff we're going to learn later in the course, we would say that they're both constant time. What's the constant? Don't care. Because loops and other things that depend on the input are going to have a way bigger impact. Oh yeah, so I was about to skip this slide because I was just flipping through things and didn't realize this was a different slide. But it's a good thing that we did because this is important. So I was just saying that constant time operations don't really matter, and that loops are the things that really matter. Oh my God, it's a loop. To handle this, we use summations. Wow, math has an application. We're going to analyze the number of steps that take place inside of the loop to get the thing that's inside of the summation. We'll analyze the number of times the loop repeats to get the summation's bounds. And then from there, we'll be able to compute a cost function for the algorithm. the algorithm gets an input n, and the cost function tells you how many steps are required on that input n. In this example, n is just an integer that is thrown into the algorithm, but you'll see in this course, and honestly in the real world, this stuff's actually super applicable. Usually you'll talk about an input of size n. So a list with n items, or maybe you're running an online game and you have n current players, something like that. Anywho, this is one step. That's one step. Now, while k is less than or equal to n, going to draw it right here. So to figure out what the summation has to be exactly, you sort of have to look at the function to give you some context clues. Here, we have the variable k increasing by 1 each time, or each iteration of the loop, and it counting until it's equal to n. As such, we use a summation with k equals 1 up to n. This was nice and straightforward, but we're going to see loops that have different conditions on them and different ways their loop counter iterates? Yeah, iterates. If there's even a loop counter at all. So it'll be your job to figure out how the loop works and sort of translate that into a summation that goes from 1 to some value. And then inside the summation, I'm going to put 2 because of these lines taking 2 steps. And then these two other lines take 1 step each. And notably, they take place outside of any loop, so their value is going to be outside of the summation. So this is an okay start, but I missed a few details. These are going to be details that you'll probably miss too, so listen up for these corrections. And they're actually all to do with that looping line 3. Checking the loop condition, like reading k, reading n, doing the comparison that k is less than or equal to n, takes 1 step. And that's going to be part of the loop. So even though there are only 2 steps in the body of the loop itself adds a step to the loop. And then something happens at the end of the program. During the loop, k has been incrementing by 1 each time. It goes like 1, 2, 3, 4, ... n minus 2, n minus 1, n. And then after the last iteration of that loop, k is going to be greater than n, but the loop condition needs to be checked 1 more time in order to make sure that the loop is actually over. Cool. And then the next step would be to simplify the summation. Using the appropriate summation identity, this sum of k equals 1 up to n of 3 just turns into 3n. And wabam. So we say that this function, as in the code, has a function, as in the math value translator thingy, of 3n plus 3. Here's an example of the loop counter not incrementing by ones. Here we see that the loop goes until, or for as long as k is less than n. N doesn't seem to be manipulated anywhere in the program, and k increments by 2 each time. So we could say that the summation that represents this loop is going to use k as its loop variable and count up to n. So maybe our cost function is going to be like maybe 2 for these two lines, plus a sum from k equals 0 up to n minus 1 of 3, because 1, 2, 3, plus another one. Another one step for checking the loop condition for the last time. This might look good at a glance, but it actually overcounts the number of steps that the loop takes, because this, like the variable counting from 0 to n minus 1, will give us a result of it taking n steps, n iterations of the loop. But since k increments by 2 each time, it's going to go to n faster than our summation would indicate. So we're actually going to define a new loop variable. We're going to call it j. We can still make it count up from 0. But then what will it count up to? Well, there's this helpful hint here. If we say that j is equal to k divided by 2, then that'll end up correctly representing the fact that k increases by 2 with each iteration. So j starts at k's start value over 2. It increases by k's increment divided by 2. And it will end at k's final value divided by 2. So I think this will work. We would still want to re-index the sum in order to make it start from 1, but that would be simple. All of the summations that we've worked with so far have not had any variables inside of them. Like, we don't have 3j or something. But if we did, well, for starters, we would actually have something like 3k. And then we would replace it with, I guess, 2 times j. It's the same idea as when we subtracted from a loop variable in the summation and then added to it in the expression inside the summation to counteract that. So that's how I would put it if I'm yapping about it to a classroom. Here's how you would put it if this were a question on an assignment. Yet another thing that you'll have to get used to for this course is reasoning about a program. We're going to be doing a lot of this from line 1, from line 5. You're sort of citing your sources here, where your source is specific lines of the program. So did I get that right? Yeah, 3 is inside there. Oh yeah, and actually we don't have to reindex the sum because our summation identity for constants lets you start at any value. Cool. So this is the number of steps inside of the loop. We add 1 outside of it to reflect how the loop will be checked. Like the loop condition will be checked once more at the very end of the loop on the last iteration when it turns out to be false. And then we add the time taken in the lines that aren't inside of any loop to get a final cost function of 3n over 2 plus 3. That thing at the bottom of the slide can be a fun exercise. The analysis would be very similar. It would involve dividing stuff by 2 and replacing the loop variable k, but it would be slightly less elegant when n is odd. I recommend trying it out. Okay, now let's check out nested loops. When we have nested loops, we're going to deal with them in much the same way as when we had single loops, but we're going to do it sort of recursively, kinda, from the inside out. What I mean by that is that we'll figure out how long it takes to run the innermost loops and then use those to figure out how long it takes to run the outer loops. So this is 1 step here, 1 step here, 2 steps inside of the loop. And this loop looks like it counts using j, incrementing it each time, up to k. Actually up to k minus 1 because of the strict inequality. The summation would count up to k if it had j is less than or equal to k. Now what does j start at? We see right before the loop it's set to 0, so it starts at 0. Adding these values because there are 2 steps inside of the loop, 1 more step each loop to check the loop condition, and 1 step after everything is over to check that the loop condition is true 1 last time, and then it turns out to be false and we move ahead. I think the slides after this simplify the inequality while they're doing the analysis. I'm going to not do that because then you'll be able to see multiple approaches to the same problem. So we've seen what goes on at the, the farthest level of indenting. We've analyzed the loop. Now we should also check out these 2 lines. They both take 1 step. So I'm just going to do +1, +1. It's easy. then I'm going to simplify at least a little bit to 3. Now we're on to the outer loop. And if we were starting from the outside going in, it would be a bit of a slog to figure out what would be inside of the summation. But since we're going from the inside out, we have already done that. It's going to look something like this. So let's see. K tends to, or it seems like K is the loop value because it gets incremented each iteration and it starts at 0. And it's going to count up to n. Oh, and I guess we should add one more step inside the loop in order to count the loop condition being checked. Next, we're going to count the steps on the layer outside of that loop, or I guess on the same level of indenting. We're going to have that last loop condition check when k is greater than or equal to n. This loop condition will be checked one last time. And then there are 2 constant time operations at the top. So f of n is going to look something like this. The next task will be to simplify the summations so that there's, oh yeah.
Should that be minus 1 like the outer?
Ooh, definitely. Yeah, since there's a strict inequality. Thanks. Oh yeah, so we want to simplify it next. For now, it's for aesthetic reasons, but later on we'll find a very good reason to simplify your summations. That'll come up with asymptotic notation. When simplifying, we're going to go from the inside out again. We'll simplify that, get a nice looking inequality for that outer loop. No, not an inequality. Get a nice looking summation for the outer loop, and then simplify that. I won't do the simplifications here because they're in the slides, and I have to rush through this a bit anyway due to the quiz. Oh yeah, by the way, like these lectures have just as much content as ones where we don't take a 45-minute chunk out of the class. So I think as a general routine, I'm probably going to not get through the Thursday lectures, but then have it just bleed into the next week. And it'll work out by the time the next quiz happens. I want to point out the formatting of this sort of overview of the program, because I really like what they've done. They count the number of steps each line takes, and when they've analyzed a loop, they just collapse the loop into one time or one line that takes a variable number of steps. Whether this is worth the effort of writing down when you're doing questions like this is subjective, but I can't deny that this is a really nice visualization of the program. Yeah, and then you simplify the summations. Note that we sort of really low standards for simplifying the summations. Once you have like an expression that's equivalent to the summation, you don't have to simplify it any further. It might be instinct to like distribute this multiplication over addition, but don't worry about it. You don't have to. In fact, it's probably better if you don't, because then that'll make it easier for the markers to see if you applied the summation identity correctly. I'm going to flip ahead a little bit because there's a really important example about if statements, and I'm not sure if it's in this lecture or the following. Okay, yeah. If statements are coming up later, and honestly, we have 4 minutes. It's like equivalent to a Friday because we don't have classes tomorrow. Let's just call it off here. Have a good weekend, everyone. Thank you.